Hello friends, let's design, build and test a Schmitt trigger circuit. So this is the Schmitt trigger circuit where the op-amp is used in inverting amplifier mode, and here the used operational amplifier is LF356. So what is Schmitt trigger is? Schmitt trigger circuit is basically a comparator circuit with positive feedback where comparator compares the two voltage levels and accordingly takes the decision at the output. So output is stable either at positive Vsat or that negative Vsat value. So Schmitt trigger is an inverting comparator with positive feedback. So here the operational amplifier is used in open loop configuration, and voltage levels that are applied at the inverting input terminal and non-inverting input terminal. So at the inverting, input voltage is applied, while at the non-inverting terminal, with the help of voltage divider network through the resistors R1 and R2, threshold voltage level is set. Now, if the input voltage is greater than the set threshold voltage value, then output voltage is settled down to the minus Vsat value. While if this input voltage is lower than the threshold voltage value, then Vout equal to plus of Vsat. So this plus and minus of Vsat values are the maximum values beyond which op-amp cannot generate the output voltage. So how to decide this threshold voltage? Threshold voltage is decided by voltage divider network. So voltage drop across the resistor R2, that is the threshold voltage value. So based upon the input voltage, this threshold voltage will be either positive or negative, as it is a differential amplifier. So accordingly, output voltage is set to plus Vsat value if threshold voltage is positive voltage. So if threshold voltage is some positive voltage, then in that case the differential voltage becomes negative. So if input voltage is greater than the threshold voltage value, then differential voltage will become negative, and that's why output is set to the minus Vsat value. While if output voltage is less than the threshold voltage, input voltage, if it is less than the threshold voltage value, in that case the differential voltage become negative, but as this is an inverting amplifier mode, output is set to the plus Vsat value. Threshold voltage is decided by the ratio of R2 and R1 plus R2 with respect to the output voltage. So here the output voltage is nothing but, as the operational amplifier is used in open loop configuration, so if there exists a small differential voltage between these two input terminals, then accordingly based upon the difference, output will be set either to plus Vsat value or the minus Vsat value. So here it is written as a when threshold voltage is positive, output is set to plus Vsat value. If threshold voltage is negative, output is set to minus Vsat value. So these are the input and output waveforms for a Schmitt trigger. So if this is a input sinusoidal waveform, then if we take the symmetrical upper and lower threshold value, then as and when input voltage is more than the upper threshold voltage value, then the output voltage is settled down to the minus Vsat value. So if Vin is greater than threshold voltage, output is set to minus Vsat value. Similarly, if according to the waveform, if input voltage is lower than the threshold voltage value, then output is settled down to the plus Vsat value. So this is a lower threshold value and upper threshold voltage. So upper threshold voltage and lower threshold voltage, it decides the if the op-amp is settled into plus Vsat value or the minus Vsat value. Now let us design a circuit. So for designing the circuit, let us consider a symmetrical Schmitt trigger circuit. Let us consider the designing of a symmetrical Schmitt trigger circuit using the Op-amp LF356. So if we consider the upper and lower thresholds to be taken as a symmetrical, it means plus Vsat, upper threshold voltage value to be plus 0.4 volt and lower threshold becomes minus 0.4 volt. So then if we set the Vsat value equal to 0.9 of the maximum value of VCC, here we'll be choosing for the designing VCC as a plus or minus 15 volts, plus VCC and minus VEE is a plus and minus 15. So with respect to this, if we set the Vsat to the 0.9, that is 90% of the VCC value, then its value becomes 13.5 volts. So our circuit should get stable with maximum value of plus or minus 13.5 volts. Now again let us choose one of the resistor value R2 is equal to 1 kilo ohm. Then using the above formula, then upper threshold value already it is set to the 0.4 volt as per the design parameter. R1 value to be equal to R2 to be equal to 1k. Then we have to design for the we have to design for the R1 value. So R1 value with calculations comes out to be equal to 32.75, but let us round it to the 33 kilo ohm. So now we need to simulate the circuit. So we'll be using operational amplifier IC LF356 with the 3 resistors as a voltage divider network R1 and R2. RL is used as a load resistance, and we'll be providing the input voltage 3 volts peak to peak as a AC signal source. So of course for the operational amplifier require the dual power supply plus 15 and minus 15. Let us simulate this circuit now. So we'll go to the simulation part. Before that we'll build the circuit. We have completed briefly the design part. Now we'll build the circuit and then we'll simulate the circuit. So for building the circuit, I will start with the placing the analog components. So in the ICs, so already I have chosen the LF356. Otherwise, just if you type here the LF and then 356. So from this I will prefer to use the LF356M model. Say it OK. So this is the IC. So with IC, with the pin numbers. So for this IC, pin number 1, this is offset null pin, which is used to remove the offset voltages and balance the input voltage. Then pin number 2 is the inverting input terminal, non-inverting input terminal. At pin number 6 will take the output. Pin number 5, it is again offset null pin, which is used to remove the offset voltage and balance the input voltage. Then at pin number 4 and 7, so at the 7 positive supply input and at pin number 4 negative supply input. So at these two terminals, equal in magnitude, opposite in direction supply voltages. So we'll be using here the plus or minus 15 volts. And pin number 8, which is not shown here because that is normally not connected. It's not connected pin number. Now let us start building the circuit. So I will choose the resistors. We'll start with the resistor value. I will select one resistor, place it here. Total 3 resistors will be required. We can make the copy of that. Along with that, from the sources family, let us choose the ground connection. So one ground connection. Along with that, power sources, we'll go for one AC source of required parameters with frequency and required voltage values. Then VDD voltage plus 15, which is to be connected to plus 7. Then one minus VE of minus 15. So minus VEE. We can do the interconnection of all these components. So before that, I will make some copies of this resistor. I will make this vertically and the resistors are required. Let us make the copies. So R1 is the resistor which is required again. So I have just changed the values of resistors. Now let us interconnect these components. So before doing the interconnection, I will just again flip this IC vertically. Choose the IC, flip it vertically. So connections will be easy. Connect these components. Let us do the connections from non-inverting input terminal. voltage divider network. Let us join this two with ground connection. Similarly to the connections of VDD, let us change its value to plus 15 volts. Let us change its value to minus of 15. Let us join this number 4, 7 to 15. Let us do the connections with output terminal. Let us call this as a load resistance. We can change the level of this R3 as a RL. And inverting input terminal with pin number 2 is connected here. So these are the connections required. So let us change the settings of input voltage. Let us make this equal to 3 volts, its RMS voltage, that is okay. Let the frequency of 60 Hz, no problem. So this is AC input voltage, minus 15. So this is what the complete connections are. So LF356M Op-amp IC. Now before simulation, let us do the connections of CRO to see the output waveforms. So where we can connect the CRO. So from the instruments bar, let us do the connections of input and output waveforms so that we can observe it easily on the CRO. So let us make the negative of both input and output to the ground connection, and let us check the output from this point. So I will change the color of this segment so that we can easily discriminate the input and output waveforms. So let's say apply and then OK. Now if we simulate the circuit, so if we simulate the circuit and see the waveforms on CRO, so these are the input and output waveforms. So we can make this bit faster. So this is the waveform. So we can change the values and we can adjust the amplitudes also. So to see the waveforms more clearly, again we can pause here and see the details. Here is the amplitude if you want. Change the time scale also to see the effects. Now if I take it onto this side, pause the waveforms, now see the effect. Now threshold values are set, but here clearly we cannot understand the effect, so it's better if we change the. So now for in this case, if we change the value of R2 from 1K to 10K, let us see what is the effect observed on the output of the CRO. So this is the waveform. I have reduced the input frequency to the 100 Hz so that easily we can observe the effect of it affects. Now if I pause this waveform and see the effect, again I will run the waveforms. See, this is the upper threshold value and this is a lower threshold voltage value. So if I just pause the waveforms and go back here, see, this is the effect. Now using the cursor, I can go to the upper threshold voltage value and this is the lower threshold voltage value. So if we see, this is the input waveform, that is a red color waveform which is connected from the input channel A. So to the channel A we have connected the input. So as long as input voltage is greater than the upper threshold value, upper threshold voltage, until it reaches the lower threshold voltage for this particular region, here as it is an inverting amplifier mode. So input voltage is greater than the upper threshold voltage until the lower threshold voltage value. So output is set to the minus Vsat value, and within this range, lower threshold till the upper threshold voltage appears, output is set to the plus Vsat value. So this is a Schmitt trigger circuit where it converts the irregular shaped waveforms into a pulse waveform where output is set to either plus Vsat value or minus Vsat value, and we can set the upper and lower threshold values symmetrically or the asymmetrically by making the respective changes in the circuit values.